mod n. So what if I told you that 2 plus 2 equals 1? Mod 3. So modulo is a really useful little operation and defines a whole bunch of really quite interesting sets. And it's also very straightforward. So 2 plus 2 equals 1 looks weird. Of course, we all know that what 2 plus 2 really equals is 4. But while that's true, 4 mod 3 equals 1. Which is nice and straightforward. So in the end, 4 mod 3 equals 1 mod 3. So 2 plus 2 equals 1 mod 3. Very straightforward. So this works for mod of all sorts of different numbers, but we usually just use simple whole numbers. So for example, the one that most of you will be familiar with to some extent is, of course, mod 60. Right? So 80 mod 60 is 20 mod 60. Very straightforward. Again, 80 minus 60 equals 20. All right, so what's 60 mod 60? That's 0. 120 mod 60? That's 0. In fact, n times 60 mod 60 equals 0, where n is in it. Every multiple of 60 equals 0 mod 60. So this gives us an interesting place, and of course, if you have the second hands on a clock, right, you will see, oh, I have a little slow for this, but you will see that once we reach 60, we mod all the way back to 0. Of course, there's also an increment clicker on the beside, on the minute beside, and dink, there we go. There's an increment clicker on the minute beside, but obviously the whole clock resets every day. So you have these sort of different mod values beside each other. We have a mod 60 to the right, we have a mod 60 again for minutes in the hour, and then we have a mod 24 in this particular case for 24 hours in a day. What this is more often used with is smaller groups. So what we can do this quite simply for is we can draw these nice little things called Cayley. I'm trying to spell this wrong. Cayley tables. Yeah, nailed it. 10 out of 10. Tables. Cayley tables. So Cayley tables are nice and straightforward, and they tell us how addition works in a particular a group mod n. Oh, and we can draw the group mod n using this simple notation. So Z n is the set of integers mod n. So Z3, for example, is equal to the set of all integers mod n, 0, 1, and 2. Obviously, we might think that, for example, 3 is in there, but 3 mod 3, if I stop bracketing, is equal to 0. For mod 3 is equal to 1, and etc., etc. Each number we go up here, we're going to increase the thing. We can draw this relationship quite nicely for all of the elements of the set within Z3. So that's all of our elements. 1 plus 1 is, of course, 2. 2 plus 2 is, of course, 1. 1 plus 2 is, of course, 0. And 1 plus 2 over here is, of course, also 0. We'll notice that every element of the final set is represented. We have a 2, we have a 0, we have a 1. If we can do addition on these guys, we can end up at any one of them, provided we do the right addition. This is going to be important because otherwise we would have trouble defining an inverse. If there's no possible way to find an element of the set that you're creating the set with, then you can have trouble making that element an inverse. So, that's a nice simple Cayley table for Z3. We can draw much nicer Cayley tables for things all the way up to like mod 8 without too much difficulty.